Okay, so when Maddie, I think it was, first suggested the idea of, hey, we need to know nuclear chem, and Knappenberger, you're an idiot because you should have remembered we didn't learn it last year. Not her words, my thoughts. Guys, I was like, 20 minutes. 20, 19, 20, we'll be fine. And then I looked at it and I was like, oh, snap. There's a lot more than 20 minutes worth of material. So guys, what I did is I printed you the notes. What I'm going to ask you to do is ignore all of the titles and the subtitles for these slides. Because frankly, I just took 4 days of general chemistry lecture and condensed them into these 3 pages. So literally, guys, what we're going to do is we are going to go over 2.5 weeks of material in 64 minutes. And, you know, Brisha was going, hey, what are we going to do when we're done with this? And my answer was, I don't know. Guys, we could still be done in 20 minutes, or we could be here until Monday. I have no idea how this is going to roll because I've never done this before. Your year last year was the first year that we ever didn't do nuclear chem. So guys, consequently, I have no idea how this is going to go. But let's jump in. I did not give you guided notes. You guys know what that means, where you fill in the blanks and things are missing. I gave you everything. So guys, the hazard to this is it might rob from you some of the learning opportunities simply because you're like, got the answers. But guys, understand that having the answers doesn't mean that you have the understandings. So consequently, guys, please ask questions. And I would encourage you to discipline yourself to engage with the thoughts rather than just seeking to have the notes. The other thing I have no idea whether these transitions are going to work because literally, guys, I just butchered 4 days worth of notes, copying and pasting and turning them into this. So guys, with that said, be gentle. Seriously, this could be a disaster. I have no idea. But please, if I'm running down rat trails and you're like, what is he doing? Bring me back and let's get into this. So guys, fundamentally, this is the deal. When we talk about nuclear chemistry, you need to understand 3 things. Why does the nucleus change? How does the nucleus change? And how fast does the nucleus change? I was especially proud of myself when I came up with this summary because I've never thought about it this way. Because this is really it. What you need to know is why does it happen, how does it happen, and then how fast does it happen? But guys, before we can answer that question, we got to talk about this. So back in the early 1900s, thinking you don't need to know dates, but back in the early 1900s, you do need to know which researcher suggested that atoms have a nucleus. Do you remember? Gold foil experiment. It was Rutherford. So guys, what happened was J.J. Thompson discovered the electron. Thompson was smart enough to know that if there's negatives, there's got to be positives. You may remember the plum pudding model where they're all gookified together. And guys, these are things you need to know. If you don't know these, you may want to scratch them in your notes. So Thompson discovered the electron. He suggested the plum pudding model, which was the working model for quite a while. And then along came Lord Rutherford, not in the biblical sense, but in the British sense. He was Lord Rutherford, and you don't need to know this, but actually, maybe you do know this, that his lab assistant was actually Niels Bohr. Did you know that? that Niels Bohr actually did the gold foil experiment, but because Rutherford was the professor, he got the credit. Anyway, so Rutherford started shooting alpha particles, positive things. Wait, did we do this last year? Okay, so particles shooting at the gold, some bounced off. Oh my gosh, there's something hard in the middle. And he discovered the nucleus of the atom. So, guys, when Rutherford started telling people that atoms had nuclei, they thought he was a quack job. Because, guys, think about what you're saying. Imagine that you never knew that atoms have nuclei, and all of a sudden you're going, hey, guess what, world? All the positive charges inside of an atom cluster together in the middle. Do you see why that's stupid? Guys, what do like charges do? Repel each other, right? Yeah. Guys, like North Pole to North Pole magnetism and electrical. Guys, positives don't cluster. Positives repel. And so here's Rutherford going, hey, good news, all the positive cluster together. And they're like, you're an idiot. And he said, I know, but I have data, so we got to trust it. And guys, the secret sauce here, which Rutherford actually didn't propose or discover, but to his credit, he was willing to stick with his results. He's like, hey, I can't explain it. I know it sounds stupid, but I've got data that suggests it's the case. We'll figure out how it works later. Guys, what they found out later is that you guys understand there are four forces in the universe. Gravity and electromagnetism are two of them. But guys, there's a third and a fourth force. One is the strong and one is the weak nuclear force. You don't need to know about the weak force. But guys, the strong force is this ridiculously strong, thus the name, force. So then the question is, how strong is it? And the answer is, the strong nuclear force is actually the force that overcomes the repulsion of the protons in the nucleus, and it causes the nucleus to stick together. Now guys, here's the thing. If gravity were as strong as the strong nuclear force, we would weigh hundreds of thousands of pounds. Did you catch that? If gravity were as strong as the strong nuclear force, then we would weigh hundreds of thousands of pounds. But guys, here's the deal. Obviously, gravity is not as strong as the strong nuclear force. But guys, the strong nuclear force is only effective over distances on the range of the size of a nucleus of an atom. It only works over very, very short distances, but it's stupid strong. Stupid strong enough that it overcomes the strong nuclear force. It overcomes the repulsion of the protons, and it holds the nuclei together. So guys, questions about that? You okay? Okay, so now guys, let's transition to the equation at the bottom, which you all should be familiar with. Who came up with that? Albert. And guys, it turns out that Albert discovered that E energy is equivalent to the mass of a substance times, we know C, the speed of light squared. Now guys, you've got to understand the implications of this because it ties back to the strong nuclear force. Guys, this does not mean that my stapler has enough energy in it that if we know the mass of my stapler in kilograms, we can then multiply that by the speed of light squared, and that's how much energy my stapler contains. That is not what this means. What it means is this. When matter, mass, gets converted into energy. Wait, I thought mass was conserved. Law of conservation of mass. No, it's not. Guys, matter can become energy, and energy can become matter. And when that happens, matter goes away, energy is released, and the amount of energy that is released is equal to the mass that was lost times the speed of light squared. Now, how do we do this? How do we convert energy and matter into energy? And the answer is we break the strong nuclear force. So when we disrupt the strong nuclear force, matter can convert into energy. And when it does, the amount of matter that's converted into energy is equal to that mass times the speed of light squared. So guys, then the question becomes this: how much energy are we talking about? So I don't know if you guys remember this from last year. So guys, how much does a big paper clip weigh? Do you remember? It's stinking really close to a gram. So if you've got 2 of them, 2 grams. I concur. Now, oh, come on. Hey, guys, I got to do this. Sorry, just a moment. So paper clips are grams, right? So, guys, the question then becomes this. Instead of steel paper clips, what if we talk instead, oh, that's my thumb. What if we talk instead about this, which is uranium? You didn't know you've been sitting next to uranium the whole year. Or did you? So guys, this is actually what uranium looks like when we dig it out of the ground. The yellow in this rock is actually the uranium. It's not pure uranium. It's actually caught up in a crystalline structure. I forget what the other element is in there, but it's a salt. It's a crystalline salt. But guys, this is what uranium looks like when it's dug up out of the ground. This is actually from Moab. Have you ever driven into Moab? And as you're about to cross the river, you look off to the right and there's all that barbed wire around what looks like an empty field. That during World War II, that used to be a uranium mine. We were so hungry for uranium that we were getting it anywhere we could find it because we were really afraid that Japan was going to come and invade the US, and we needed to figure out a way to fix that. And so, guys, we were looking for uranium wherever we could find it. But then the problem was once things settled down and once we figured out there were better ways to get uranium, we just walked away from Moab and left all this uranium ore sitting all over the place for people to then stumble into and get really sick. So we decided to clean it up. And that's what those have you seen those train tracks that follow, you know what I'm talking about, the ridge? Those are actually the train tracks that haul this stuff out of the ground and to places where they store it.
Hey, Cosper, please check out.
Who? That was you? Oh, thank you. Just watch the screencast. So, guys, with all of that said, here's the trick. Make this uranium pure and then get this much of it and convert it into energy, and guess what happens? Hiroshima gets vaporized. Guys, they've done the calculations, and to our best math, when they dropped the bomb on Hiroshima, which actually contained kilograms and kilograms of uranium, their best estimation is between 0.7, 7/10 of a paperclip, between 0.7 and 2 grams of uranium was converted into energy. What happened to the rest of it? The rest of it simply blew up and was scattered across the remains of Hiroshima and actually killed more people than the people that died in the blast from radiation sickness later. But only about 2 grams of that uranium was actually converted into energy. The rest of it was just rained down over that area as uranium dust. And that did more damage than the other. So guys, the idea is that you get in a sense of how strong the strong nuclear force is. Because guys, when we muck with that thing, energy gets converted into matter. And matter gets converted into energy and really crazy stuff happens. By the way, if you're interested, do you also understand that energy can convert into matter? It goes both ways. That was the Big Bang. So the thing that banged the singularity was actually just a bundle of energy. And as it expanded, it cooled. And as it cooled, energy was condensed and converted into matter. And that's where all the matter in our place came from, was from that thing expanding and cooling. Oh, yeah. It's true. Yeah, right? Yeah. Crazy stuff. And guys, I should say this. You can believe that and still be a person of faith. I know there's this weird tension that says creation and evolution, and if you believe in evolution, you can't believe in God, and Big Bang is anti-God and all this other stuff. Guys, wait until you get to college and people actually start challenging you on that, even at BYU. I've had professors at BYU in the biology department tell me to my face that when they go to work, they check their faith at the door, because they can't do science and believe their faith. It was really strange. Guys, we really can't talk about this other than to say, if you're a person of faith pursuing a degree in science, do not let anybody ever tell you that you can't live in both camps, because guys, it's not true. And if you ever want resources and links, please reach out to me. Some of the brightest minds in science are also people of amazing faith. And please don't let I faced that in college. Please don't let anybody take you down that road. So, strong nuclear force, are we good? Okay, so now this. Guys, the strong nuclear force can change in one of two ways. The strong nuclear force can go boom. That's called fission and fusion. These are high energy events. You'll find out in a minute that fission does not happen naturally anywhere in the universe. Fission only exists because Robert Oppenheimer and his buddies down at Los Alamos Labs figured out how to get this to go in the 1940s. Because fission does not happen naturally anywhere in the universe. Fusion? Not just in Spider-Man movies. Guys, fusion is what drives every star in the universe. Light elements are fusing together into heavy elements. That does disrupt the strong nuclear force. Matter is being converted to energy. Guys, look it up. Our sun loses trillions of pounds of mass every day, because hydrogen is being converted into helium, and when it does, a little bit of mass gets lost, and that mass converts into energy, and we call that sunshine. But the idea is that our sun is converting mass into energy at the rate of, I think it is trillions of pounds a day. You'd have to look it up, but it's crazy. So, but guys, here's the thing. Fission and fusion are not the only ways that the nuclei, I'm going to glove up in a minute, but I'll just point right now. Guys, there's another way, no, I'm going to do it now. Guys, there's another way that nuclei change. And it's not fission or fusion, it's what's called radioactive decay. So we should talk about this. Oh, that's upside down. Are you guys familiar with the idea of a Geiger counter? So guys, this is a Geiger counter. The way that it works is there's actually a tube inside this thing that is charged. I forget the gas that's in there. Anyway, it doesn't matter, but you can actually see it. Can you see the tube through the window? Guys, what's going on is it's really a lot like a fluorescent light bulb. But instead of applying a current that makes it glow, when radioactive particles penetrate the tube, it creates a little bit of a current. and you know from lab, currents can be turned into information. And so every time a little current happens inside of there, there's a computer that feels that current and it makes it beep. Now guys, here's the thing. If you listen, it's beeping. What does that mean? It's being hit with radioactive particles all the time. And guys, so are we. We are being, imagine how small this tube is, and then imagine that scaled up to the surface area of your body, right? It's probably thousands of times the surface area of this. Whoa. And you can hear how often this gets hit. Imagine you. Guys, you are being pelted with radioactive particles all the time. There are even radioactive particles that travel through the entire Earth and never touch anything. They're so small and so fast that they're raining through you right now. Thousands of them are passing through your body this instant. And you'll never know because they're so small and so fast that they don't hit an electron or a nucleus the whole way through your body, the whole way through the Earth and out the other side. These things are everywhere because you can hear them, right? You hear the clicking. There's a name for this. This is called background radiation. Background radiation is the radiation that we were exposed to just because of where we live. So where does it come from? It comes from the sun, it comes from lights, it comes from radioactive stuff, because we are always being bombarded with radiation. So guys, why do we not then get cancer? Because if we have high enough doses of these things, you probably are going to get cancer. So guys, why do we not get cancer as a result of this bombardment of background radiation? And the answer is because our bodies are stinking cool. There are so many error checking systems in our bodies that when radioactive particles interact with our DNA and they knock things around, there are these systems in our body that say, this is broken, throw it away, because we don't want to make more of this because it's going to turn into cancer. It's crazy. Wait until you take this class, biochemistry, where you learn about those error checking systems. It will change your perspective of life. It's unbelievable. Anyway, so guys, we don't get cancer because our body has all these systems in them that actually fix the problems or throw out the problem before it becomes a problem. Understand though, there's limits to that error correcting system, and eventually our bodies can't keep up. And like the people in Hiroshima, they got exposed to so much radiation that their bodies couldn't keep up, and frankly, they died of cancer months and years later. So anyway, you guys good on these ideas? Okay, so guys, this then is what we're going to do. We're going to go high energy, we're going to go low energy, and then we're going to talk about how fast, and then we're good. So guys, first of all, high energy changes. The first is what is called fission, which is not what Christian is going to do over the weekend. Get it? I'm going fission. Spencer wasn't here. I had to give it a shot, right? Could we turn that into a joke and put it in the thing? What is a chemist, what is a nuclear chemist's favorite pastime? Fission.
That's pretty good, actually. I like it.
Yeah? Is that okay? All right, that's all I had. So guys, fission is the process where nuclei break apart. As this happens, we end up with smaller and smaller fractions of atoms. Where does this happen? This happens in nuclear power plants, and it happens in nuclear weapons. So guys, literally, in every nuclear power plant on the planet, there's literally a nuclear bomb that is going off in a controlled way that keeps it from becoming a bomb. The question is, how does this work? So guys, look at the picture. This you need to know on the test. So over there on the left, we've got a uranium-235 nucleus. That's the stuff that we try to get out of uranium ore. And what we do is we purify that. You guys know this story, right? How do we purify the uranium? And the answer is we centrifuge it. we literally spin it in centrifuges, and the lighter uranium-235 comes to the top, and the heavier, more predominant isotope 238 goes to the bottom. And so we literally separate these based on mass in centrifuges. Well, guess who has a bunch of centrifuges? Iran. Guess who's not supposed to have a bunch of centrifuges? Iran, because they signed an agreement that said that they were going to discontinue their uranium enrichment programs because we were afraid they were going to make bombs, and they said they wouldn't, and if they needed uranium for peaceful purposes, they would buy it from us. But it turns out we found with satellites, they're uranium centrifuges. You guys know how this story ends, right? Oh, shoot, all of their uranium centrifuges imploded on themselves. Oh, it was a computer glitch. Who possibly could have taken down all the computers in all of Iran's centrifuges? Ah, if only we knew who was capable of that. Isaac, well played. Well done. Isaac is actually in the witness protection program, and his name's not actually Isaac. Yeah, that's right. Yeah, they actually couldn't. They actually they tricked one of the Iranian scientists to plug in a USB stick into it because they couldn't get through the firewalls. So they tricked this guy to stuck in a jump drive and click on something, which then opened up all the holes and allowed somebody to get into all of their control computers and melt the entire system down. So, guys, how does this work? And the answer is this. Guys, the flashy things are meant to represent energy. And we start with uranium-235. Turns out uranium-235 is relatively unstable. And when we blast it with a neutron, how do we blast things with neutrons? Dynamite. Literally, guys, the bombs that went off on Hiroshima and Nagasaki, literally the trigger were explosives like dynamite. But when we do this and when we fire neutrons at uranium-235, that neutron sticks to the nucleus and it creates uranium-236. Uranium-236 is highly unstable. The strong nuclear force breaks and it flies apart. When it does, it creates two lighter elements. A little bit of mass is lost. Again, 2 grams over Hiroshima. A little bit of mass is lost that converts to energy. But here's the secret sauce. Guys, what else comes out of the explosion? 3 neutrons. You see where this is headed. Those 3 neutrons then break down 3 other nuclei, and so on and so on and so on. And the next thing you know, you've got a nuclear chain reaction, and goodbye Hiroshima. Guys, this also provided one of the reasons that we got the bomb before Germany did. You guys understand this, right? That most of the bomb makers in the United States that helped us win the war were actually German and Polish refugees as Hitler was running across across Europe, trying to grab a hold of these Jewish European people in Germany and Poland and other places. They fled, and they fled to the United States. And they came here and they said, hey, we were chilling with Hitler and his people, and guess what they're trying to do? They're trying to create this bomb based on this weird thing called fission. And if they get that, we're done. So Albert Einstein actually wrote a letter to the president, right? He's European, but he fled to here. And he said, hey, guys, Germany's going to do this. And if they get the bomb, the world's going to change forever. And frankly, thankfully, people listened to Einstein and we got to work. But guys, one of the problems with this is that it would fizzle out. When the initial explosion would happen, it would expand so quickly that the neutrons couldn't keep up with the uranium that was spreading out. So we figured out a way to slow the explosion immediately so that it wouldn't just expand and fizzle. Actually, what we did is we took the uranium and we hid it in charcoal. carbon. Graphite. They hid it in graphite, and when they did that, the graphite would keep the thing from expanding too quickly, and we got a bomb instead of a. Germany didn't figure that out, and that's why we're still here. But this is the idea. So then the question becomes this: how do we take this explosion and turn it into a nuclear power plant? And guys, the answer is this. If you want to slow down this reaction, what you actually have to do is take neutrons out of the system. Does that make sense? What makes this thing run out of control? The neutrons. How do you slow it down? You put neutron sponges into this reaction. Now, guys, understand this reaction in a power plant happens at the bottom of kind of what looks like a swimming pool. And what they do is they take the uranium or the plutonium and they infuse it into rods, fuel rods, and then they stick it down into this thing and they use it to generate heat, which then creates steam, which then spins turbines, which then generates electricity. But they can speed the reaction up and down by sticking these ceramic rods into the reaction. They're literally made of clay, but they're made of a special clay that absorbs neutrons. So if they want to speed the reaction up, they lift some of these control rods out, more free neutrons, faster reaction. You want to slow it down, stick more control rods in, fewer free neutrons, slower reaction. You get the idea? Okay, so guys, I'm going to switch the order of these slides. This one's a video slide, and I just want to show it to you, but it goes here. So this is actually kind of what we're talking about.
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142.
Oh shoot, let's be clear, when that nucleus splits, strong nuclear force, right? It's overcome. Sorry.
Nuclear uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amounts of energy in the form of heat, light, and ionizing radiation, an atomic explosion.
That kind of jive with what you were thinking? Okay, so then guys, the other high energy nuclear event is what we call nuclear fusion. Instead of breaking nuclei apart, we put nuclei together. This is what fuels, if you will, all of the stars in our galaxy, in our universe. Literally, these are big balls, typically of hydrogen, that are fusing elements together to make heavier and heavier elements. But guys, understand the mass of the element that is formed is slightly less than the mass of the elements that go in, and consequently, there's a little bit of mass that's converted to energy, and that's sunlight and all of that. Guys, this is also what happens inside of hydrogen bombs. During World War II, it was fission bombs, and we blew up Hiroshima and Nagasaki. Shortly after that, both us and the Russians figured out how to do not fission bombs, but fusion bombs. Guys, these are the bombs that we can use to vaporize islands. I don't know if you know about this. There are Polynesian cultures right now that don't have a place to live because we either vaporized their home or we vaporized a neighboring island, and their home is so radioactive they can't live there anymore. Yeah. We did. Yeah, but you gotta, Cade, right? You're like, how could especially a country that claims to stand on the moral high ground. Forgive me, but we've done some pretty slimy stuff. We were so desperate to win the war that it was literally at all costs. And we figured, forgive me, but hey, if we have to move, a village of Pacific Islanders to the United States because we need to test our weapons, small price to pay. So we vaporize islands out there. Yeah, it's crazy. But you're in Utah. You understand the whole idea with the downwinders, right? So the idea was that we knew that when we were testing nuclear weapons in the United States, that the same way as in Hiroshima and Nagasaki, that the explosion was going to create a cloud of radioactive particles. And these radioactive particles were going to rain down over the neighboring areas. And so we had a choice to make, and it was literally this. If this is the United States, West Coast and East Coast, all of the nuclear research was happening on the West Coast, down in New Mexico, up in Washington State. This was where all the research was happening. But if you think about it, which directions do the winds blow in the United States? West to east. All of our prevailing winds blow west to east. So when they originally started talking about where should we test our nuclear weapons, they said we should do it on the Atlantic coast so that the predominant winds blow all the dangerous stuff out in the Atlantic Ocean and it'll be safer. But then they realized, remember, this was pre-interstate highway. We didn't have I-80, I-90, I-70. It took a long time to get from Massachusetts to New Mexico. And they're like, if we want to keep up with the Russians, we don't have time to be driving our stuff to the East Coast. So let's just blow up all these test bombs here in New Mexico, Nevada. Let's just blow them up there because then it's faster. So, but wait, won't all of that radiation then rain down on populated Western states? Yeah, but it's worth it because we got to keep up with the Russians. And it actually got, hey, what? Not in this class. Possibly, yeah. Sorry, you saw me flinch because I have a Parker, but not Johnson. Keel, but not Johnson. No. Yeah, sorry. Yeah. So, sorry, long story short. So, guys, they started blowing up bombs in New Mexico and this area. And sure enough, the winds carried the debris across the United States. Check this out. It was so bad that the Kodak company that made film, specifically film to do x-rays, Kodak sued the United States government because so much radioactive fallout was traveling across the United States that New York State, Rochester, New York, where they were making their photographic plates for x-rays, was receiving so much radiation out of the air that it made their film unusable because the radiation was exposing their x-ray film. Isn't that crazy? So how did our government respond? They actually said, oh, that's interesting. Could we please see those photographic plates? Because based on the exposure, we can figure out how our bomb explosions are working. And they paid Kodak for those exposed plates because they could get data out of it that would help them understand the efficiencies of their explosions. Crazy, right? Yeah, crazy. Look all this up, guys. It's all out there. Anyway, so this is called fission. Also hydrogen bombs. We don't need to get into that in great detail, but there you go. You guys good? Okay, so now, I really wanted to show this to you, but we don't have time. So we'll do.
So in this box.
All right. So now, guys, low energy things. These are ways that nuclei change that is not fission or fusion. This is what is called nuclear decay or nuclear breakdown. You know this by the name radioactive decay. It's radioactivity. So guys, radioactive decay happens when unstable nuclei release protons, neutrons, and electrons. Shall we pause for a moment? What is releasing protons, neutrons, and electrons? Unstable nuclei. What's in the nucleus of atoms? Protons, neutrons, electrons? No, but guess what? They can still come out of the nucleus. There are no electrons in the nucleus of an atom, and yet the nucleus of an atom can actually release electrons. Do you hate it? You should. But guys, they do this in an effort to become more stable. So guys, you need to understand this. Take a look. This is what is called the nuclear band of stability. On the x-axis, we have number of protons. So that's basically the periodic table from hydrogen up through, where's element 80? Mercury. And then guys, on the left-hand side, that is not mass. That is actually numbers of neutrons. So guys, let me explain this to you. Here's what's going on. You'll notice that at first, well, let me just tell you. So guys, this is a 45 degree angle. You understand that graphically a 45 degree angle represents 1-to-1 ratios so long as the units are the same on the scales. So guys, that line right there represents a neutron to proton ratio of 1-to-1. Now, each one of those blue dots represents a nuclei that is not radioactive. It's stable. Well, guys, where are all the dots down here? On the line? Yeah? And maybe you remember this from last year. Hydrogen has 1 proton, well, that bad example. Helium has 2 protons, 2 neutrons. Lithium, 3 and 3. Beryllium, 4 and 4. Boron, 5 and 5. Carbon, 6 and 6. Nitrogen, 7 and 7, and so on. So guys, the super light elements are stable with a 1-to-1 proton to neutron ratio. But then you'll notice that what happens is as these get heavier, the stable nuclei depart from the 1-to-1 ratio. They need more neutrons in order to be stable. Notice that it's pitching towards neutrons. They need more neutrons in order to be stable. The question is why? And the answer is this. What's the charge of a neutron? Nothing. So it doesn't push, right? Neutrons don't push on protons. But guys, neutrons do strengthen the strong nuclear force. So they strengthen the force that holds the nucleus together while not creating additional repulsion. So neutrons have a stabilizing effect on the atom's nucleus. So guys, this then is how this works. All of these elements that go squiggly through here, all of those elements are not radioactive. But guys, if you have elements that are here, or if you have elements that are here, those elements are radioactive. The reason is because they're not stable. So guys, let's talk. Over here, if we've got an element right there, and if it wants to move over towards the band of stability, what does it need to gain or lose in order to do that? It needs to lose protons. Now guys, what if we've got one over here that needs to move in that direction? It needs to gain protons. So the question is, how do they do that? How do they lose and how do they gain protons? And guys, the answer is radioactivity. That's how they do this. So the question then is, how do you gain and how do you lose protons? Well, let's talk first about losing. Let's talk first about losing protons. So guys, in order to lose protons, what you do is go through what is called alpha decay. Let me just give this to you. Guys, alpha decay will stop there. Guys, alpha decay actually involves the release of a helium nuclei. So literally what you've got is you've got a nucleus like uranium that's just hanging out going, hey, yo, I'm a nucleus, but I've got too many protons. And so this nucleus goes, I got this. I got an idea. How about if I spit out a couple, a helium nucleus? Guys, a helium nucleus is 2 protons and 2 neutrons. So literally what happens is a helium nuclei, 2 protons and 2 neutrons, comes flying out of the nucleus of this atom, and the number of protons goes down. The number of neutrons goes down too, but the important bit is the number of protons goes down, closing it in on the band of stability. So you guys, you ready for a weird thought? If you have a helium balloon, guess where most of the helium on Earth comes from? From this. Most of the helium that we have on the Earth actually comes from the alpha decay of radioactive particles. There's really no other source for helium here on Earth. Yeah, very soon. I don't know if you know this, but the United States actually has helium reserves. What we've done is we've taken salt mines and we have actually used these abandoned salt mines and we pump them full of helium. Helium is quickly becoming one of the substances that we know we can't do without, and it's not to fill birthday balloons. The problem is that so much of the important chemistry and physics that we do right now, MRI machines are cooled with liquid helium. Computers now run so much more efficiently at super cold temperatures. So if we run out of helium, we're done. Like it's over. And so I don't know if you guys have seen this. In the last few years, they've been rationing birthday balloons. You ever run into that? You go to the store, Zurchers, and they say, we can only sell you 3. The reason is because there are times when we start to see our emergency reserves of helium start to deplete, and the government pulls back and they make helium so expensive that Zurchers can't afford to sell it to you anymore. So yeah, helium's a big deal because we have a very limited amount of it here on Earth. So guys, what this looks like then, is there a video next? Did I not get it in there? Shoot. Hold on a second. Hold on a minute, guys. I'd really like you to see this video. Oh, wait, it's not there. Here and here. Nuclear chem, decay, movies. Shoot. Gosh, this video is so good. Let me see if I can just YouTube it. Sorry, just a minute, you guys. This is worth watching. So, alpha decay. Oh, can we get them all? Ooh. That does not look like anything I want to watch. Ooh, small atoms, no. Let's just try alpha decay. Sorry guys, this is really good. Oh yeah, here we go. Okay, well this isn't what I was thinking of. I haven't seen it. Let's hope that this doesn't get weird. But this is what we're talking about.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy.
Wow, that was really boring. But guys, that's actually it. That was horrible. Somebody posted that? But actually, you do kind of maybe get the idea that you've got this big old nucleus that's just got too many protons to be stable. And literally what happens is a helium nucleus comes out. Now this thing is fewer protons and closer to stability. That was the worst animation I've ever seen in my whole life, but that's the idea. Yeah. Yeah, that's a good question. And the answer is because helium is super stable. If you get into chemistry in college, Kate, if you get into chemistry in college, what you'll find out is that, you know, when we draw the electrons, we do all this pretty stuff, right? But when we draw the nucleus, we just draw a ball. Not true. The protons and neutrons in the nucleus of an atom are actually organized like electrons. They're in orbits, they're in structures, they have fixed numbers that can fill those things. And just like the octet rule makes some electron structures stable, there are also nuclear structures that are super stable. And helium is one of those structures. So you won't get into that until probably your junior or senior year in college, but that's the case. So guys, that was alpha decay in a nutshell. We need to go on and talk about beta decay. Beta decay is funny, and I really want to get into this. Guys, beta decay goes the other direction. Instead of the number of electrons going, or I'm sorry, instead of the number of protons going down, it goes up. What? Guys, it turns out that you understand alpha decay. Stuff goes away. We get stuff goes away. Well, guys, it turns out that protons can actually magically pop into existence in the nucleus of an atom. And this is actually how it happens. Let me pick a new, let's do carbon. So imagine you've got a carbon atom, and that would be 6 protons and 6 neutrons, and that's a carbon atom. Well, guys, if this carbon atom goes through beta decay, actually what happens is one of these neutrons magically turns into a proton. Oh, yeah. So now all of a sudden, we've got 7 protons and we've got 5 neutrons. But guys, here's the trick. When that happens, an electron goes flying out of the nucleus at thousands of miles an hour. But guys, this isn't science fiction. This actually happens. Neutrons can magically turn into protons. And when that happens, the number of protons goes up, leading that element to get closer to the band of stability. Yeah.
Wouldn't that become a different element?
It does. Carbon turns to nitrogen. Yeah, and the same would be true in the other direction, right? Like if we had uranium, which is 92 protons, and 238 minus 92 is 146. 146 neutrons. If this goes through alpha decay, which is a helium nucleus, the number of neutrons goes down to 142, and the number of protons, sorry, that's here, and the number of protons goes down to 90, and so uranium actually turns into thorium. Yeah, is that okay? Okay, then guys, one last thing and we're almost done. The last type of radiation that we need to talk about is actually gamma decay. Guys, gamma decay is not a particle. Gamma decay is actually energy like light. It's the most penetrating type of radiation. It's scary, crazy stuff, but it's really just high energy light. So when a nuclei goes through gamma decay, its identity doesn't change, its mass doesn't change, nothing changes. The only thing that changes is it loses a little bit of energy. You should know this though, gamma decay never happens on its own. Gamma decay is actually a relaxation process that takes place after alpha or beta decay. So a nucleus goes through alpha decay, that creates stress, and then it releases that stress through gamma. Could be beta, doesn't matter, and then it releases the energy. So guys, those are the only 3 types of radiation you need to know, alpha, beta, gamma. So guys, what then is making this thing click? alpha, beta, and gamma decay going through that tube. I'm going to show you quickly. So guys, this is interesting. So uranium, right? Why does this thing click? What's hitting it? Alpha, beta, or gamma, right? Guys, there's so many radioactive particles flying out of this thing. Alpha particles, helium nucleus, beta particles, and I'll be honest, I lie to my general chem kids. This doesn't give off gamma radiation. If it did, I wouldn't have it in the house. I tell my general chem kids they do because they don't know the difference. But guys, crazy sauce, right? But now watch close. Why did it slow down? Yeah, not deflected, they're getting absorbed. Guys, alpha particles are so big and fat and slow that they can't get through my hand. And so this is full exposure. This is minus the alpha particles, because the alpha particles only penetrate about, I think it's like a 0.5 centimeter of flesh, and then they get stuck. But something's still getting through, right? Is faster than background. Those are the beta particles. To get rid of the beta particles, we actually need a sheet of lead. So this is full exposure. This is minus alpha. This is minus beta, because the lead is so dense that the beta particles can't get through. So now we're closer to background, but that's the idea. The lead isn't quite thick enough to shield from all the beta, so it is a little bit faster, but you get the idea. You good on that? Okay, one last thing. How long does this take? How long does it take for something to go through alpha, beta, or gamma decay? And guys, the answer to how fast, whoa, I really don't know what to do about that. Oh, shoot. What happened? Cancel. Okay, so guys, the last question is, how long does it take for this to take place? And guys, the answer is half-life. Let me explain to you half-life by doing this. So here's the idea. We're gonna pretend that this chunk of uranium is pure, and pretend that it weighs 100 grams, and pretend that it only goes through alpha decay. Got it? Pure, 100 grams, alpha decay. Now guys, let's do this. If uranium goes through alpha decay, it loses 2 protons, so it turns into thorium, yes? Okay. Now guys, imagine that the half-life of uranium is 1,000 years. It's not. I made up the number. So guys, here we go. We've got a chunk of uranium, and it's 100 grams, and it's going through alpha decay, and we're moving through time, and it's now 1,000 years later. What does this weigh? Still weighs 100 grams. But it's not 100 grams of uranium. What is it? It's 100 grams, it's 50 grams of uranium and 50 grams of thorium. Guys, that's the idea behind half-life. Half-life is the time that it takes a radioactive element to half of it to turn into another element. That's our working definition of half-life. It's the time that it takes half of it to turn into something else. Good? Now this, 1,000 years, 50% thorium, 50% uranium. After another 1,000 years, all the uranium's gone and now it's all thorium, right? No. Here's what happens. After another half-life, the 1,000 years, now 3/4 of it is thorium, but 25% of it is still uranium. Guys, why does the rate at which this breaks down slow down? Concentration. So the idea is, guys, in theory, this will never go away because you can always have a half of a subsequently smaller half, and it never goes away. It's an asymptote. So guys, it looks like this. What happens is more like this. So guys, graphing half-life across the bottom and percentage up the side. When no time has gone by, we have 100% uranium. After one half-life, it's 50-50. After two half-lives, it's 75-25. After three half-lives, it's whatever that 87.5 and 12.5. And it gets smaller and smaller and smaller. But this is an asymptote. It never falls to zero. You never fully lose the substance. Get the idea? So guys, this may be a problem that you get. It reads like this. 50 grams of plutonium decays for 7,200 years. What is the mass? What mass of plutonium remains at the end of this time? Remembering, because my Gen Chem kids learned this, that the half-life of plutonium is 2,400 years. Guys, I would encourage you to solve this by drawing rocks. Hey, look, it's a chunk of plutonium. And guys, this chunk of plutonium weighs 50 grams. I'd encourage you to do this with me. This chunk of uranium weighs 50 grams. Then guys, 2,400 years later, what does the rock weigh? But how much of it's plutonium? 25. Because the question is, what is the mass of the plutonium? Then we go through another 2,400 years for a total of 48. And now this is 12.5 grams of plutonium. Then we go through another 2,400 years, running out of space, dividing it again in half, and it's 6.25 years. But guys, that's where we're done. Why are we done? Because those total up to 7,200 years, 72,000 years. So 24, 48, 72, that's the amount of time. Each time it cuts in half. So after 72,000 years, 6.25 grams of it is still plutonium. You get the idea? Okay. Guys, that's it. We have about a minute left. Brescia, I think you should run to missed calls. Guys, we go lunch, and then we go fourth period, and then we go goodbye. No school on Monday for you, although most of you, I suspect, are coming to do practice exams with other AP teachers. Tuesday, guys, multiple choice practice. Thursday, oh, wait, stop, hold on. One other thing, this is important. So, guys, I have received permission on that Monday when your test is in the afternoon to cater a lunch. Where do you want it to be from? Typically, we do things like wingers, Mo Bettas. Think about it. We'll talk next week. Have a great weekend, you guys.